Hey, you 13s. It's good to see you all. Okay, so big lesson today, folks. We've got to lesson 10 in the acid-base sequence of lessons, and we're now starting, the really, really challenging aspect of acid-base. The two hardest calculations that you'll ever have to do in A-level chemistry are redox titrations and buffers. So we're going to begin the process today of starting to build our understanding of buffers and be able to begin the process of stepping into those calculations. Okay, so I'm going to share my screen. Let's crack on. Let's go for that one. Okie dokie. Right, I said that I'd add the link, and I also definitely need to do the pop the chat out. There we go. So I know that's running. Don is there. Amazing. Pop out chat. Let's get rid of that. I hope you guys can hear me all okay. Okay. Hello. All right. So let's crack on. Okay, guys. Big lesson. So now I'm going to actually attempt to not focus on the calculations today. I just want to begin the process of you understanding what a buffer is and how it functions. So we've been noticing this buffer region appear in some of our acid-base graphs seen in previous lessons. So just to go back to this particular question, we came across these graphs, and I was just highlighting that in a certain few of them, we were seeing buffer regions appear. So in this particular scenario, we had a buffer region appearing at the weak acid strong base titration. And then we also had another one over here bearing that because we had a strong acid and a weak base. But notice that they were on opposite sides of the graph. Now that's quite interesting. So I'm hoping that by the end of this lesson, we'll be able to explain why those two regions are on opposite sides and how they've been created. So my learning objectives for today, I'm going to be looking to, number one, I need you guys to know that a buffer is a mixture of a weak acid or base. Now that's important, a weak acid or base and its salt. I need you to understand how a buffer functions using equations to support our answers. I want you to know both methods for making buffers. And the last one is I want you to know their uses and the example of blood as being a natural buffer. You can add that in actually. It's quite nice for me to mention that. This is a natural buffer. Okay, so a buffer. So what we need to do is, first of all, we need to define what a buffer is. So step number one. Now, you guys may have heard this word before. I wonder if anybody on the chat would be able just to post an example of where they may have heard it outside my lessons, whether or not you've seen it in any home context or any other co-curricular, alternative curricular context in any other lessons in school. I just wonder whether or not anyone's actually heard of this. Foods, by the way, are a key one. So what is a buffer? So a buffer is a solution, and I'm going to draw this out as an image. Yeah, a buffer is a solution. So first of all, this is a buffer aqueous. Yeah, a buffer aqueous. So this is a buffer solution. Yeah, a mediator. Ain't that the vampire? Ria, that's amazing. My YouTube videos buffer. Aha! So true, Ivan. What a fantastic example. Buffering. Yeah. And do you know what, Ivan, I'm going to come back to that example because it's such a good example. Ain't that the Vampire Slayer? That's Buffy. Yeah, not Buffer. A mediator. Yes, well done, Nikita. But it's not the definition. But it is. A mediator is a good word there, but we need definitely to be able to develop that word to understand what it means. So a buffer, step one, this is the definition. And what we're going to do is I'm going to use my image to build the definition. Yeah, so we've got number one, a buffer is a solution. A buffer is a solution. Okay, so it's a solution. Now, what can it do? Now, what it does is if I add an acid to this, like HCl, if I add an acid, now if we have a solution like water, now water we know is not a buffer. Yeah, if I have H2O in a beaker and I add a small amount of HCl, we here already know that the pH of water, assuming 25 degrees Celsius, and it's pure, is 7. So there's water. What prediction would we make about what's going to happen to the pH when I add a small amount of acid to my water? What's going to happen to that pH? Let's see how many people can give me that on the chat. So what's going to happen when I take a beaker of water and add a small amount of HCl? What's going to happen to my pH, please? Nice to give you guys a bit of time to think. Lower the pH, lower pH value. I like it. Decrease. Thank you, Dana. I like it. pH drops. Love it. We've got a good understanding that if you add an acid, the pH is definitely going to decrease. Yes, but this is the thing. It's not just going to decrease. It's going to decrease a lot. We know that a small amount of HCl can make a massive difference to water. We can even run the calculations for it. Let's just, for fun and games, run a dilution calc. That's what this actually classifies as. So step number 1, I've got 100 centimeters cubed of water, H2O. We know that it has a starting pH, assuming STP, of pH 7. What we're going to do is we're going to add to this, we're going to add 1 centimeter cubed of 1 mole per dm cubed, 1 centimeter cubed of 1 mole per dm cubed HCl. And we're going to go, bitch, let's just run the calc. It's always nice to do so. I'd like you all now to pause the video and calculate the new pH, please. So the answer. It's a dilution. We're adding pure water to a small amount of HCl. So this is C1V1 equals C2V2. Okay, so our original concentration of the HCl, the original concentration was 1. The original volume was 1 centimeter cubed. Right, my new concentration is the question mark, but my new total volume is going to be 101 centimeters cubed. Okay, so rearrange. So C1V1 divided by V2 is going to give me C2. I can insert my numbers. My calculator has been a proverbial nightmare of late. 1 times 1 over 101 gives me C2. Nice and easy numbers. Yeah, turn my calculator on. I've ordered a new calculator off Lazada, so that'll be turning up soon. So that's going to come out as 9.90 times 10 to the minus 3 moles per dm cubed new HCl. Right. We know that it's a monoprotic acid. It is fully ionized in water. So we know that the concentration of this guy is going to be the same as the concentration of the H+. So all we now need to do is minus log answer, and I get minus log answer, and I get a pH of 2. Amazing, look at that. So we've just gone from a pH of 7 to a pH of 2 with 1 centimeter cubed of acid. That be crazy. Yeah, we've just turned pure water at pH 7 down to pH 2 with the addition of 1/100th of its volume. That is bonkers. Now, what now you realize is that acids are corrosive. At high concentrations, they're corrosive. At lower concentrations, they're irritants, but they're also very damaging. Yeah, acids and bases like to destroy proteins. They like to destroy polyesters. They like to destroy destroy acids or bases, depending if they're in the picture. They like to destroy all kind. They destroy everything, and it's a real problem. So what that means is, what we needed to do is we needed to be able to regulate pH. So we created a buffer. Buffers is a solution, bullet point number 2, that resists, now that's important, resists change in pH, looks like something else, resists change in pH. Notice I'm using the word resists and not that it stops the change, not the word stops. Yeah, that stops change. No, it resists change in pH upon small additions of both acid and bases. Right. So that's the definition of a buffer. A buffer is a solution that resists change in pH upon small additions of both acid and bases. Okay, so how is that possible? So let's look at the picture again. We know for a fact that if I add hydrochloric acid to a solution, it is going to produce H pluses. And we all know, thanks to the chat, that the pH is therefore going to drop. Now, what that means is, in order for me to resist that, I am going to need something else in the beaker that is going to counteract it. What I am going to need is a base. So in a buffer, I need, change my color, I'm gonna go for blue. Yeah, I need a base. Yeah, so I need some base molecules. I need a base. Now, what that is, that base in the buffer, if I add acid, that acid will react with the base and neutralize it. Okay, but the problem is in the definition, it says of both acids and bases. So what I need to also be able to do is be able to add a base to this beaker as well. So I'm going to add a base. And in order to resist that effect, I need something else in the beaker. I need an acid. So I need in one beaker, in one solution, I need an acid and a base that won't react together. That's what I need. So, okay, how is that possible? And I wonder if anybody here, if I was in class, I'd be asking for any insights, and we'd be talking about, previous lessons where we've seen alternatives to acids and bases, or maybe family-related acids and bases. And in order to achieve this, what we're going to do is we are going to put in our solution, we are going to add either, now we've got two choices here, guys. This is where it splits. This is my learning objective. Yeah, both methods of making. Yeah, and also the fact I'm actually doing, no, I'm not tackling that one yet. I'm doing the first one. There are two types, weak acid or base, and it's salt. There's a hint in the metal oxides and hydroxides. Is it a weak acid and a weak base? I don't know. Ria, no, it's not. It's not, and that is the wrong answer. Emma, metal oxides and hydroxides? No, definitely not. Metal oxides are basic as well, Emma. Yeah, a weak acid. That's pulled it out the bag. Well done, Dat. What we're going to do is we are going to add a weak acid. Let's choose one. Let's add ethanoic. Let's add vinegar. Let's keep it easy. We're going to add ethanoic acid, and we are then going to add its conjugate base. Sodium, its conjugate base. We're going to add a conjugate base, which is something like CH3COONA. And they're going to ask you to name these, by the way. So that would be ethanoic acid. The name, of course, is change my color. Ethanoic acid. Ethanoic acid. And we're going to add to it sodium ethanoate, the conjugate base. I like it. These don't play together because they're family. The word conjugate means family, yeah? And to be created from somebody. So we've got an acid and its conjugate base. And what that means is that I am going to create an equilibrium. I'm going to set up the equilibrium between ethanoic acid and its conjugate base. There. So here is our acid, and here is our CBAS. Here's our base for the buffer. Yeah. Now, in order to have a buffer, I need to have reasonable quantities of both of these. Yeah. So that's just an assumption. There's an assumption for you guys. Nota bene. Assumption. No, it's not an assumption. It's the wrong word. Nota bene. For a successful buffer, we need large amounts of both acid, weak acid, and its conjugate base, its salt. I'm going to actually steer away from using the word conjugate base eventually. Yeah, salt. Now, just to mention, I talked that there were two types. My learning objective number one, a weak acid and its salt. Yeah, but we can also do this from a basic perspective as well. If I use a weak acid and its conjugate base, I am going to produce what's called an acidic buffer. Yeah, these two here will create an acidic buffer. That means acidic buffer. This means it will have a pH, give or take, I always like to say 4.5. It's a really good number to have, but it's below 7. The reason being is the base, gotta be careful. The key ingredients are it's a weak acid and it's salt. We know that a weak acid can have a pH anywhere from kind of 2.3 up to like 3.5, and the conjugate base is about 8.5. Between 7.6 and 8.5, well, the acid is going to dominate and it's going to pull it down. Yeah. So there's no point in me doing that. But so we're going to create an acidic buffer doing this. We can also create a basic buffer. Yeah. We can also create basic buffers. How do you create a basic buffer? Requirements are a weak base. Example, e.g., ammonia. It's a great example. Ammonia aqueous or an amine comes up a lot, especially because it links this. Mr. Duncan, you said that the acid dominates and pulls the pH down over the conjugate base. Why exactly is that? It's a good question, Ben. The reason being is because in reality, we realize that it's simply a case of who has the lower. If you run the calculation for the weak acid, you're going to end up with a pH roughly between the 2 and 4 mark. Yeah, usually 3-ish. But the pH of a 1 molar solution of the conjugate base is not that acidic, anywhere between 7.6 to 8.5. I tend to go on the higher end, but it's closer to 7 then. And since it's closer to 7, it's just kind of, it's a scale, isn't it? If you put the 2 in line, I shouldn't really do a pH scale, a vertical pH scale. Yeah. If you have it's tempting to show the buffer regions on the graph at that point, actually, Ben. You realize that the buffer regions are low. Yeah, the buffer region, when you have a weak acid and its conjugate base is low, it's because there are still large quantities of H plus in the mixture. And of course, the conjugate base is not actually removing any of them. It is to a small extent, but not really very well, hence why the slight slope in it almost being horizontal. It's a difficult question to answer that, Ben. I hope I've given you an answer which is reasonable. Yeah, the acid is still contributing H plus to the system, which is what we're counting. And the conjugate base is not doing a great job of mopping it up. It'll shift the equilibrium, it'll allow the equilibrium to move when more H plus is added, hence the buffer action, but itself doesn't really contribute a huge amount of the pH. Oh, I hope that helps. It's a horrible question. Great question, Ben. I'll try and do some maths for that, Ben, to be able to give you a better answer. Anyway, requirements for the weak base, the basic buffer, weak base, and of course, and its salt, and conjugate acid. I don't really like using that. I'm going to put salt, yeah, salt, brackets, C acid, conjugate acid. So what would the conjugate acid be for ammonia? I'd like you guys to post on the chat. I know that there's a delay, but it doesn't matter. You can still post it then on the chat, so I know that you're getting it right. So the salt of ammonia, or the amine, yeah, the main one, of course, is like ammonium chloride. Yeah, that's the conjugate. Whoosh, that's the conjugate acid of ammonia if I've added HCl. Yeah, for an amine, let's give a specific amine. Let's go for methanamine, or old name, my preferred name, methylamine. Yeah, I'm going to add HCl. I'm going to add the HCl over there. Yeah, if I add HCl, I'm going to form the salt of it. Yeah, and that's going to form CH3NH3Cl. Yeah, so there's the salt of those. And then you learn to adapt those. Don't learn loads of them. Just learn one of them, understand what's going on in terms of the salt creation, and then you can create any. Now, basic buffers are very unusual to come up in exam questions. You may see one or two in multiple choice, but not in long answer. So I'm going to be focusing this lesson today on for the weak acid, for the acidic buffers. So, okay, let's go back to my learning objective. So number one, we know we can definitely say we can now do that bit. Yeah, those questions will appear. You know, they'll give you an acid and say, what do you add to this to make a buffer? And you can figure out what you're adding in order to achieve that. Now we need to explain how a buffer functions using the equation. Okay, so, and this equation is how they function. So if, let's now do a new subheading. Okay, explaining buffer function. Buffer function. Okay, so what we're now going to do is we now need to look at this from a question perspective. Yeah, so they're going to say, Nikita adds a small amount of HCl to her acidic buffer. Explain change in pH. So, okay. So what we need to do is we need to be able to say what the change in pH is going to be. Yeah, that's a separate question. It's 1 mark for saying what's going to happen. So wait, with Ben's question, it's like that will take up the H plus preventing pH from decreasing too much, or am I confused? No, that's correct. That's correct, Ria. It's exactly what's going to happen. So she's got it. Let's focus on the ethanoic acid. So we had, I'm going to color code this now, guys. So we've got ethanoic acid in the beaker, and that is our acid for the buffer. This is our buffer acid. Yeah, buffer acid. We've also got in the beaker its conjugate base. So CH3COO minus. This is our buffer base. Okay, so what's now going to happen now that she's added her HCl? So number one, the HCl is a source of H plus. So the answer, I'm going to do it in black, answer. So the H plus, step number one, the H plus from the HCl is going to react with the conjugate base. It's going to react with the conjugate base. And that is, so I'm now going to do this and change my color again. So this is Nikita's addition, H plus from HCl. That's, we've stated what the HCl is providing, which is H plus, and it is now going to react with the conjugate base. That there is step number one in my explanation. If that's the case, what's the point in adding the ethanoic acid as well to resist pH on the addition of base? Yes, correct. Well done, Dat. So that's step number one. So the H plus from the HCl is going to react with the conjugate base. Now, what's now going to happen is that H plus is therefore going to be removed. So H plus is removed. Now it's removed because what this is now going to do is we all know that this reaction here, I'm going to try and color code this, the reaction that's now happening is going to push the equation in that direction. It's not very clear, is it? Because my line was too fat. It's going to push the equation in this direction. Yeah? Now, and the H plus gets removed. It disappears. And we know that that is where pH is founded. Yeah? H plus is how we measure pH. And we are now going to push the equilibrium in from right to left. And we're going to be creating more of the buffer acid. Yes? And the H plus is therefore being removed. H plus is removed. So that there, I'm going to try and color code this as best I can. So step number 1, I'm going to do in pink. Step number 1, yeah, is it's going to react. The H plus is going to react with the conjugate base. Yeah? Next, in pink, step number 2, the H plus is now going to get removed. Yeah, you don't change the equation. The equation is good. I'm just telling you that that process removes it. And it does this by shifting the equation. Yeah? So the H plus is, I'm going to put therefore removed. Therefore removed. It's therefore removed. The step 3, the equilibrium. The equilibrium shifts from right to left. Shifts from right to left. Right. So we're going to create more of the ethanoic acid concentration is therefore going to increase slightly, and the buffer base, the conjugate base concentration is going to decrease slightly. Now, what we now need is we can now figure out, based on that understanding, what's going to actually happen to the pH here. Yeah, we realize we have removed the H plus that was added in the HCl, but I have shifted the equilibrium towards the buffer acid. What's now going to happen to the pH of my buffer? So number 4, yeah, buffer 4, by the way, green, of course, is explained in the shift. I ought to do it in dark green. Oh dear, that didn't work very well, did it? There you go. It's linking that bit to here. Yeah. So if you add loads of HCl, would the equilibrium not be able to recover? Or would you eventually bring it back to the original? No, Kayun, we will talk about breaking buffers. We will indeed, changing buffers. Yes, you can break a buffer. And in fact, you watch it happen in the titration curve, Kayun. In the titration curve, you can literally watch the buffer region get broken. So we see an immediate spike in the pH as we add the strong base in this reaction. Well, why wouldn't that spike? Why wouldn't that graph just continue in a linear fashion? The reason being is, as soon as I've added some of it, yeah, there's the initial spike. As soon as I've added some of it, I now am going to create the conjugate base. And that's now going to create a buffer. And that buffer is going to then slow the change in pH. But then eventually, if I keep adding my alkali, I'm going to break it and you're going to see a big spike. Isn't that clever? Love it. Great link to the graphs. Beautiful chemistry. Okay, so now what's going to happen to the pH? So the pH, of course, it is going to change. So I wonder if anyone can tell me what's going to happen to the pH. Let's say let's call the original pH, just for fun. Let's just make one up. Original pH, let's go for the most common, about 4.5. Original buffer pH, 4.5. Let's just call it 4.5. It's a nice number. It's a nice and acidic buffer. What's going to happen to that number now that I've added HCl to it? It is going to change, but the question is, in which direction and how much? And can you explain why? So on the chat, guys, 3 questions. Question number 1, is the pH going to increase or decrease? Number 2, is it going to increase a lot or by a little? And then question 3 is explain why it changed at all. And that requires a bit more thinking about the equilibrium, what's being created, what's being destroyed. Wonder how many people are going to get it. I'm going to give you your answer. See how many people know it. So it is going, the pH will drop. I should capitalize, really. The pH will drop. I've added an acid. Of course it's going to drop. Come going to become more acidic. The pH will drop, but only by a tiny amount. Hence the word by a tiny amount. Hence the word resists. A buffer it can't stop pH change. Nothing can stop pH change. But what it can do is it can resist it. It can turn those big changes from pH 7 to 2. Yeah, so by the way, so what kind of numbers would we expect? Just curious. So the original was pH 4.5. It will drop after addition. After HCl, I'm going to get a new pH of something like 4.35. It's going to drop by the tiniest of numbers, maybe even less, depending on the volume of buffer you've got, depending on the amount of acid you're adding. Now, of course, it will break eventually. You can break it if you add enough. Something that Kayun picked up on. And by the way, using these equations are beautiful. It's so nice to understand how a buffer is functioning. We can look at this now from the basic perspective. I think the pH will increase. No, Ben, it's not going to increase. I was not meant to post that. Love it. It's definitely going to decrease. I've added an acid. If I add an acid, it will decrease. So the question is, why has it changed at all? If the H plus has been removed, yeah, if H plus has been neutralized, why would it change at all? The reason being is I have created more of the weak acid. And we all know that in terms of running weak acid calculations, if you increase the concentration of your weak acid, the pH will drop. Now, we're also removing the conjugate base as well, but it has very little impact. But it's the idea that we are still creating an acid which is still going through dissociation, but of course, at a 10 to the minus 5 scale. So it does drop because we're creating more weak acid, which will go through, therefore, more dissociation because it's a higher concentration. So as Kayun mentioned, if you add a lot of H+, will it eventually react with all the conjugate base? Yes! Ria, if I add enough acid, I will use up all the conjugate base. Hence, oh, love it. Where is it? A successful buffer needs large amounts of both conjugate acids, weak acid and conjugate base, because we need large amounts of them. That's there. Large amounts. Because if we only had a tiny amount of it, then you're just going to break the buffer immediately. We want them to be in massive excess. Loads and loads and loads and loads and loads of them. Yeah. And anyway, so let's do the basic buffer. Okay, so question number 2. Explain how, shouldn't slope it, no point. Explain how a basic buffer of, let's do ammonia and ammonium chloride resists. Explain a basic buffer of ammonia. Explain how a basic buffer of ammonium chloride resists pH change on addition. pH change on addition of. Let's add a base. Let's do the base side. On addition of small amount of NaOH. Okay, so first thing I'm going to do is I'm going to create my equations. The first step that I would do, yeah, so guys, I'd like you to pause the video, please, and have a go at creating it yourself. Remember the bullet points that we went through in the previous one? Step 1, create the equation that the buffer is established, that that the weak base and conjugate acid are going to create, and then followed by what's going to be produced, what is being added by the sodium hydroxide, what is that then going to be reacting with, don't forget to mention if it's being added or removed, and then talk about the shift in equilibrium. So the equation is ammonia and ammonium. Now that's the clever twist, isn't it? They gave us ammonium chloride and people are going to add the Cl and you don't want to. So that's the equation. That's the equilibrium that has been established. We've got my weak base and I've got my conjugate acid. We have now added, so bullet point number one, the OH minus ions from NaOH will react with, right, who's it going to react with? Oh, it's going to react with the positive side. Of course it is. It's going to react over there. It's going to react with NH4 plus ions. It is therefore going to be removed. The OH minus is therefore removed. Oops, therefore removed. Right. Okay, if I react this, if these are going to react, it's going to become ammonia. Oh, and water. There's the other product that I'm going to get, guys. If I want a balanced equation, there you go. Yeah, it's going to form water. So we now need to say the equilibrium. I was just checking the chat window. The equilibrium will shift from, in this case, from right to left. From right to left. It's going to shift that way. Shift from right to left. Right, what's going to therefore what's going to happen to the pH now? Well, there's a great rule. I added a base. It will increase. It will. The pH will increase by a tiny amount. Will increase by a tiny, looks like I put Timmy, by a tiny amount. Right, so let's have a look at my learning objectives. Let's go back to those. Know the definition of a buffer and what it contains. Very reasonable, number one. Number two, understand how a buffer functions using equations. Definitely, got to that point. Both methods of making, we have not done this one yet. Uses of buffers, we can add that one and blood as an example. So I can do my fourth learning objective today. So the uses of buffers, yeah, uses. Let's just quickly finish off my lesson. Yeah, uses of buffers. So number one, in the making of dyes. So when you make any dye, dyes are very pH sensitive. Yeah, very pH sensitive. So if you change the pH, you'll often change the color, if not destroy the color altogether. So in the making of dyes. Number two, in the making of drugs. In the making of drugs. Again, making of drugs. By the way, dyes is a preferred answer. But again, as drugs have become more and more complicated, they have now become very pH sensitive. Some drugs are sold as the salts, and some drugs are not. So they're also pH sensitive. It can also be used. Used in foods to regulate pH. Do you know what? I'd really like you. I'm not going to put the foods one down on the list. What I'd like you to do, guys. Actually, you know what? I will add that. I'm going to add it in red. It's not really a preferred answer, but it's true. And this comes back to Nikita's original post. She put regulators. She put mediators. Ah, so close. Number three, in foods. In foods to regulate pH. In foods to regulate pH. These are called, to regulate pH, these are called preservatives or stabilizers. More commonly called stabilizers. 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 Is it stabilizers? Stabilizers. Have a look at your Coca-Cola cans. They all contain buffers to regulate. Are dyes like angry indicators? Yes! Oh, okay, and that's so true. Angry indicators. Yeah, kind of. Yeah. Yes. They're more stable and less toxic. But yeah, kind of funny. Just to mention, I said at the start of this lesson that I loved one of my favorite things for this lesson was that Ivan said YouTube buffer, and I loved that. So guys, YouTube, whenever you guys watch a video on YouTube, it's so nice to see a context here, which is very, very different. Whenever you've got your YouTube video up and you see your pie chart. Yeah, so the question is, why does it say buffering? It says buffering because it wants, if you lose the internet connection, yeah, if you cut the internet off, it'll still play. It is resisting a negative effect, the stopping of a video when the internet slows down. What happens if what happens if the internet speeds up and you suddenly get more data? Well, it's not going to fast forward the video. It buffers. The buffering process stores a set amount of data in the system, so it will resist the changing in speed of the video on the addition of large or small amounts of data. Way, love it. That's so cool. Love that reference. You'll never need that for exam. And blood is a natural buffer. I'm going to add blood to another lesson. I've only got 4 minutes left, so I'm going to end it at that point. But guys, this has been a lot of fun. Really enjoyed it. I hope you found it useful. I will post your questions on the classroom. I will post your questions on the classroom as always. If you have any questions at all, please send me a message on Google Hangout and I will reply. Have a great rest of the day, guys. See you soon.